Let's make indefinite integrals easy, and I'm going to show you several shortcuts as well. Starting off with, what is an indefinite integral? So if I've got the integral of some function, f of x dx, this is going to be the integral that gives me an antiderivative back. It's going to give me a function back, f of x, and there's always this constant on the end plus c. So it actually gives me this family of functions back. It's my antiderivative because if I take the derivative of that answer, d dx, of that antiderivative plus c, here's why we've got that random constant on the end, why we get a family of functions. The derivative of the antiderivative is f of x, which is inside of my integral here, and the derivative of c is equal to 0. So I can go back and forth between my indefinite integral and my antiderivative. Let's go ahead and go through several examples. We are going to look at constants, polynomials, square roots, x's in the denominators, exponentials, logarithms, and trig functions. Here we go. Let's do some constants first. So let's say that we are looking for the integral of 3 dx. When we take these integrals, we are going back to the variable of integration. I'm really looking for the antiderivative of 3, and the antiderivative of 3 is 3x, but I want to put in that random constant plus c. I can check all of these answers. If I take that derivative of 3x plus c, the derivative should get me back to that function in my integral, and it does, so equals 3. Let's do another one. Let's say that we've got the integral of, let's do e dx. E is the natural base e, 2.71828. There's no variable here for my function. So the integral of e dx is going to be just e times my variable of integration plus a c. Let's say that we've got the integral of pi d theta. Now in this one, my variable of integration has changed to theta, but I'm going to do the very same thing. I'm going to get that constant back times the variable of integration. This time it's theta, so I end up with pi theta, and don't forget your plus c. Let's move into some polynomials. For example, let's say that we have got the integral of x squared dx. I'm looking for the antiderivative, so we need a power rule for integrals. That power rule for integrals looks like this. So the integral of x to some power n dx is equal to, I'm going to bump the power up by 1. So it's x to the n plus 1 divided by that new power, n plus 1, and then plus a c. Let's apply this to the integral of x squared. I'm going to increase that power by 1, so x to the 2 plus 1 divided by that new power plus a c. So we're going to write that answer as x to the third divided by 3 plus c. Here comes another example. Let's say that we've got the integral of 5x cubed dx. I can go ahead and take that 5. It's just a constant multiplier, and I can pull it out in front of my integral. If I do that, I'm going to be left with something that I need that power rule for. So I'm going to put that 5 on the outside. So 5 times the integral of x cubed dx. This is going to equal 5. So I've got that multiplier out in front. And let's go ahead and apply that power rule to x cubed. This is going to be x to the 3 plus 1, all divided by my new power, 3 plus 1, and then don't forget about that plus c. So what do we really have here? I've got 5x to the 4th divided by 4 plus c. Let's say that you've got a couple of terms in your integrand. So let's put together one like this. I'm going to do, I don't know, let's do 3x squared plus 4 dx. As I am integrating, I can integrate term by term, which makes it really nice. Technically, I'm doing the integral of 3x squared, and then I'm adding that to the integral of 4, but I can go ahead and just do this all at the same time. Now I've got this constant multiplier of 3 that's going to come out in front. Let's go ahead and integrate x squared. As I integrate x squared, I'm going to bump that power up by 1. So it's 2 plus 1 or 3, so that's going to be x cubed divided by my new power 3. Plus, now let's go ahead and integrate 4. 4 is a constant, so it needs to be multiplied by my variable of integration, which is an x. So I get 4x, and then outside of everybody, I get that plus c. So this answer becomes, I can cancel those 3's, and I get x cubed plus 4x plus c. So we can do polynomials, we can integrate them term by term, but what if I had a variable in the denominator instead? Let's say that I've got 1 over x, that's supposed to be a 3, 1 over x cubed dx. The very first thing that I want to do is to rewrite that so I can use the power rule. I'm going to bring that up into my numerator as a negative power. Do need some more room here, so I can rewrite this as the integral of, let's bring that up to the numerator, so that's going to be x now to the negative 3 dx. I can still use my power rule just as I had done before. So as I use my power rule, it becomes x to the negative 3 plus 1 divided by my new power, negative 3 plus 1, of course, plus a c on the outside. If I add those together, negative 3 plus 1 is negative 2 divided by negative 2 plus c. Let's go ahead and finish it off by moving this x to the negative 2 down into the denominator so it's got a positive power. I'm going to do that, and my answer then is going to leave me with just 1 in the numerator. I can put the negative sign out in front, and I've got the 2 still in my denominator, and I'm going to bring that x now with a positive 2 also in my denominator plus a c. The next one's going to have a radical. Let's see how we can use the power rule with a square root inside the integral. So I've got the square root of x dx. I can change the square root into an exponent. This is really x to the first power inside my square root, and I've got a 2 as my index. A cube root would be a 3 as what we call the index. So rewriting this, I want to get that power of x. It's going to be 1 divided by 2 dx. Perfect. Now I can go ahead and apply my power rule. So x to the 1/2 plus 1 divided by my new power 1/2 plus 1, and then of course plus a c on the outside. I need to deal with that 1/2 plus 1, and I want to write this instead as an improper fraction. 1/2 plus 1 is 1/2 plus 2 over 2, also known as 3 over 2. So we end up with x to the 3 over 2 divided by my new power 3 over 2 plus c. I still need to clean this up though. I want to get a radical instead of a rational exponent, and I also want to get that fraction out of my denominator. It's easy to deal with the fraction in the denominator. I am dividing by 3/2, so instead I want to multiply by the reciprocal. I want to multiply by 2/3. So that's going to become a 2/3 times in my next step. So there's that one. Let's next deal with this x to the 3/2 power. Here's a really easy way to simplify these rational exponents where the numerator is bigger. Watch what I do. I can rewrite this as x to the 3/2. 2 goes into 3 one time, so 3/2 is the same as 1.5. This tells me that I have x to the first and x to the 1/2 power, which I can easily write as an x. The 1/2 power is a square root. so that x to the 3/2 power becomes x radical x, and then we've got our plus c. I'm just going to finish this off and rewrite it all in green so you can see that this is my answer, 2/3 x radical x plus c. Okay, so we've done constants, we've done polynomials, we've done some negative exponents, we've done some radicals. Let's go ahead and move into exponentials and logarithms. I promise these are going to be easy. I'm going to start off with my very favorite integral. It's also my favorite derivative because it's so darn easy. The integral of e to the x, I just get e to the x back. And then of course, plus a c. Let's change that e to the x just slightly and say that I've got an e to the 3x dx. In order to get this to work out correctly, I need still the exponential back. So this is going to be e to the 3x all divided by 3 plus c. So I can follow this pattern along by getting my exponential back and dividing by that common multiplier. If you want to double check me, you can use a chain rule to differentiate and go backwards. Let's see if you can do this one. So if I had e to the 4x dx, what would you get? If you want to follow along with me or check your answer, you're going to get the exponential back, e to the 4x, but you're going to divide by that 4 plus a c. Now there's a method called u-substitution that you could use on problems like this, but we're going to save those for ones that are just a little more complicated. This is a really great workaround. My video link is in the bottom and also at the end of the video. Okay, so how'd you do? So e to the 4x all divided by 4 plus that c. We also want to be able to work with logarithms, and I'm going to work with them in this form. So if you remember, the derivative of the natural log is 1 over x. That means I can work my way backwards. So the integral of 1 over x is going to be the natural log of x plus a c. One more little detail here. The domain of 1 over x is anything but 0, so all real numbers except for 0. However, the domain of the natural logarithm, if you don't remember what it looks like, I'll draw you a tiny little graph. It looks like this. The domain is anything greater than 0. So I'm going to put absolute value bars around my x to make sure that my domain is correct. Let's do another one. So if I were to do the integral of 1 over x plus 2 dx, this is still 1 over x plus or minus something. The plus or minus something doesn't change anything. So I'm still going to get a natural logarithm back. So I get natural logarithm of whatever I've got in my denominator, and I can go ahead and write that in absolute value bars, x plus 2, and then plus a c. What if I also had a constant multiplier for this one? I'm going to do the first step with you. So let's say that we've got the integral of 3 divided by x minus 1 dx. I'm going to do the first step with you, and that's to go ahead and move this 3 out in front. I can think of this as a 3 times 1. So that's going to leave me with 3 on the outside of the integral, 1 over x minus 1 dx. Go ahead and do this one and then check and see if you match my answer. As I do this one, I end up with that constant multiplier 3. And now I'm going to go ahead and integrate 1 over x minus 1. 1 over x plus or minus something means I've got a logarithm, a natural logarithm. So I end up with 3 times the natural logarithm of that quantity in the denominator, and then plus a c. How'd you do? Whether you got this one correct on your own or you were able to follow along with my solution, you're doing great so far. Next, let's take a look at some common trig integrals. In this chart, I've got all of our trig derivatives. You should have these memorized because you are going to be looking for these answers to our derivatives as common trig integrals. If you've got them memorized, you're going to be able to work backwards really easily. For example, let's say that we've got the cosine of x dx. I'm going to look for that as somebody's derivative. There it is. It is sine's derivative. And I know that I can work backwards by doing an integral. So that means that the integral of cosine of x is going to be equal to the sine of x. And then, of course, I want to put a plus c in there. If I had a multiplier inside of my cosine, let's say that I had a 5x inside here dx, I'm still going to go back to the sine function, but really similar to the pattern that we saw before. I'm going to end up with the sine of, I'm going to leave that 5x there. This is a really, really nice shortcut. And I'm going to divide by that 5 and then plus my c. This is really similar to what we did with our exponentials. Let's do another one that's similar to this. Let's say that we've got the integral of secant squared 3x dx. So I know that secant squared is somebody's derivative, and it is right here. It is tangent's derivative. But my argument, what's inside the parentheses, is a 3x. So I'm going to write my answer as the tangent of 3x. And I divide by that common multiplier, divided by 3, and then plus a c. So as long as you've got these common trig derivatives memorized, you can work your way backwards. Let me move up a little bit more so we've got more room. Here comes another one. This time, let's say that we've got the integral of the sine of x dx. Take a look at that chart of derivatives. Whose derivative is this? Well, it is almost cosine's derivative, but it needs a negative sign. So you could rewrite this with an extra negative sign. I can put a negative sign outside of the integral and a negative sign inside the integral. Once I've done this, I can recognize negative sine x as cosine's derivative. So I end up with my negative sign. And what I've got there underlined in blue is the cosine of x. And then, of course, I've got my plus c. So really what you want to memorize here is that the integral of sine is negative cosine. So negative cosine x plus c. See if you can do this next one. This next one's going to be the integral of the sine of pi x. What would you get? If you want to follow along with me, I know that I'm going to get that extra negative sign. So the antiderivative of sine is negative cosine. I'm going to leave the argument on the inside, so that's going to be a pi x, but I've got this constant multiplier inside, which is my pi, so I am going to divide by pi and then add that c plus c. I'll bet you're doing great. Again, whether you're able to do this on your own or follow along with me, you're exactly where you need to be. For the next one, let's say that we have the integral of x sine of x squared dx. For this one, we're going to need u-substitution, so you're going to want to watch my next video here. You guys are doing great. Thank you so much for watching.